teneffüslerde kayıt durdurulmuş. Bir parti kaçmış. Azıcık bir 15-20 dakikalık kısmı galiba kaçmış.
Kaydedilmemiş mi?
Yani geç başlatılmış teneffüs bittikten sonra. Öyle söyleyeyim.
Anladım. Ne yapabiliriz bu hususta?
Evet hocam. Teneffüslerde kaydı durdurmazsak problem olmuyor. Tek seferde izlemesi de daha kolay oluyor bizler için.
Tamam, o zaman Başak orada mısın?
Evet hocam buradayım. Ben kaydı başlattım. Bitirene kadar da kapatmam o zaman. Tamamı 3 saatlik ya da 4 saatlik bir kayıt olmuş olur.
Tamam.
Tamam.
O diğer kısmı da zaten yani PDF olarak yükledim ben. Anlatabildim mi
Tamam hocam,
arkadaşlar?
teşekkür ederim.
Sağ ol. Evet. Bir de
hocam.
so we posted the first homework on Monday. So I guess you got the homework, right?
Yes, we did, but can we say something about it?
Yes, go ahead.
Is it possible for you to extend the deadline for a little bit, because we have midterms from data structures, homeworks from data structures, and signals and systems. This lesson has a homework. System programming has an homework. OS has an homework to the same day. So it is very difficult for us to complete them all.
Yeah, but we are also going to have a kind of midterm after 3 weeks, I guess. So we need to, assign another even homework before the midterm. So we cannot extend it, unfortunately.
Okay, then. Is midterm going to be an exam or something like homeworks?
It looks like homework, but of course it's going to be an exam format.
No,
so
but
it's going to be a online midterm exam.
No, are you gonna land it so we can solve it in our home without the cameras and all that, or just a
With
normal?
the camera is real time, so online is going to be.
Okay.
So that's why I need to assign second homework before the meeting, so we don't have time to extend, okay? Any other question? All right. And let's start our lecture then. Let me share my screen. Okay. Can you see it now? Hey guys, can you see my screen?
Yes, we can see.
Evet.
Okay, so we are gonna start with the Laplace transform today. So this is one of the first transform that we're gonna learn. And Laplace transform. So why we need transforms? And it's because, sometimes we're going to, so the main idea in this course is to analyze the system, performance or the behavior and so on, or to obtain a response of a system for a given input. So sometimes analyzing in time domain, most of the things happen in the time domain. Actually, everything, all the real-time system works in the time domain. And let's say we have a system h of t or a signal, doesn't matter. So sometimes you cannot see the behavior of this signal or system in time domain. And we need to convert or transform this system into another domain There are many domains, of course, but in this course we are going to only consider two domains. One of them is, of course, the time domain. The second one is the frequency domain. So that's why we need to convert these signals or systems from time domain to frequency domain. In other words, we need to transform. So actually the conversion or transformation from time domain to the frequency domain is a forward transformation, and the inverse of that is called inverse transformation. It's from frequency domain to the time domain. So one of the most popular transformation among this conversion is called Laplace transform. So we are going to learn the Laplace transform. So before that, let's define the Laplace transform, the definition. So definition, it's the tools that makes it possible to represent arbitrary input f of t in our case in terms of exponential component. So simply, Laplace transform is an analytical tool, mathematical tools that makes it possible to represent our signal input, which is f of t in our case, in terms of exponential components. So we're going to represent any kind of signal in terms of exponential components. That's called Laplace transform. So the forward Laplace transform. Let's define it. So we have f of t in time domain signal and f of s. We're going to say L is the Laplace transform, where in this case s equal to sigma plus j omega. So this is a complex number, as you can see. So what's the equation for this transform? Is f of s is equal to, from minus infinity to infinity, our time domain signal f of t times exponential minus st dt. So this is our Laplace transform from time to frequency domain. Of course, we have the inverse operation, which we call inverse Laplace transform. So inverse is the opposite, and is basically to convert f of s back to the f of t. How do we obtain this f of t? F of t is equal to 1 over 2 pi j c minus j infinity c plus j infinity, our frequency domain signal, and f of s times exponential st ds. So this is our inverse Laplace transform. In this case, C is a constant that is chosen to ensure the convergence of integral. Okay. So this Laplace transform is a bilateral Laplace.
So sorry, can you go up a little bit?
Yes. Bilateral Laplace transform pair is to summarize. F of s is equal to Laplace of time domain signal, and the inverse is f of t inverse Laplace f of s. These are the two Laplace transform pair. So, or we can show this in the following form: f of t bidirectional bilateral f of s. Okay, so this is the theoretical background, and let's have an example to understand this Laplace transform. Example: find Laplace transform of the following signal. We're going to have three examples. The first one is our delta function. The second one is a unit step function. The third one is cosine signal that you may guys know. Cosine signal u of t. So that's the question. Find the Laplace transform of the following signals. The first one is delta of t. The second one is u of t, which is unit step function. And the last one is cosine omega 0 t ut. Okay, so let's solve it together. The first one is delta function. So basically, we are going to find out the Laplace transform of delta function. So according to the definition, what's the definition says? F of s is equal to this integration. Let's write down again. F of s is equal to, from minus infinity to infinity, f of t times exponential minus st dt. So we're going to just put the value right down there. From minus infinity to infinity, delta of t times exponential minus t dt. Remember, guys, what was the delta function? It was a function that has a value only at t equal to 0, and the rest was equal to, remember, for the other t values equal to 0. That's why from minus infinity to infinity is equal to 0, except for t equal to 0. So if I put this value delta 0 minus s0, you know, this is already going to be equal to 1, and this is equal to 1, and the result is 1 for all s values. So the result is actually fs is equal to 1. This is how you obtain the Laplace transform of a delta function. So visually it looks like this. So that was the f of t in the time domain. If you convert this into the frequency domain, this is the frequency domain, s f of s actually is equal to 1 for all the value of s from minus infinity to infinity. So it looks like this. So you can interpret this result by saying that, you know, for instance, this information is only, it was focused on one point, which was t equal to 0. But when you convert this signal into frequency domain, S domain, you spread this information all over from minus infinity to infinity. So as if you are zooming out this information. So in the time domain, it was only focused on one point, which was t equal to 0. But when we convert this signal or information into the S domain, frequency domain, as you see, we spread this information all over the S values from minus infinity to infinity, as if you are zooming out. So this kind of transformation we use a lot in many applications, especially for the computer vision, you know. Okay, that was the first one. The second example. Second example was, remember guys, it's f of t was equal to u of t. So the question is, what is the Laplace of this f of t? So we're going to follow up the similar steps that we did in the first example. Just write down the Laplace equation, which was equal to, from minus infinity to infinity, f of t times exponential minus st dt. So we're gonna just plug in the f of t, which was equal to u of t times exponential minus and st dt. Okay, let's remember how the unit step function looks like. And it was equal to, remember guys, a unit step function. It was something like this. So that means from minus infinity to the 0, it was equal to 0. That's why it has a only non-zero value for t greater than or equal to 0. That's why we can change the lower limit from 0 to the infinity. And for this range, it's equal to 1 times exponential minus st dt. So how we're going to solve this integration is equal to 1 over minus s times exponential minus st and the limits are from 0 to infinity. So if you evaluate this integration for these limits, it's going to be equal to 1 over s times exponential minus infinity minus exponential 0, right? This is equal to 1, and this is equal to, sorry, this is equal to 0. This is equal to 0. And this is equal to 1, right? So that means 1 over s times 0 minus 1, and the result is 1 over s. And this integration exists for when the real part of s is greater than 0. So that's the second one. The third one is cosine signal that you guys know. It's equal to cosine omega 0t ut. And the question is, what is the Laplace transform of this signal? Okay. So now I guess you guys know what to do is to write down the definition of the Laplace transform from minus infinity to infinity, f of t times exponential minus st dt. Okay, so we need to do some trick here before we start to evaluate these guys. And you know, you can write down the cosine omega 0t in terms of exponential, right? Which is equal to 1 over 2 exponential j omega 0t plus exponential minus j omega 0t. So we use this property and we are going to plug into here, which is going to be equal to f of s is equal to and minus infinity to infinity 1 over 2 exponential j omega 0t plus exponential minus j omega 0t ut times exponential minus st dt. Okay, because of this u of t, remember from the previous example, so the limit is gonna change from 0 to infinity. We get rid of this u of t, and we can take 1 over 2 out of integration because of is a constant. So what we end up was a exponential j omega 0t plus exponential minus j omega 0t times exponential minus st dt. Okay, if you multiply this 1 over 2, if you distribute this, is from 0 to infinity exponential minus s minus j omega 0t plus exponential minus s plus j omega 0t times dt, right? Okay, so now we are ready to solve this integration. For each part is going to be equal to 1 over 2 times 1 over minus s minus j omega 0 times exponential minus s j omega 0 t. and plus plus 1 over minus s plus j omega 0 times exponential minus s plus j omega 0 t. And the limits are from 0 to infinity. Right? Now let's evaluate these results for these limits, which is going to be equal to 1 over 2 times 1 over s minus j omega 0 times 0 minus 1 plus 1 over minus s plus j omega 0 times 0 minus 1 again. So the result is, if you solve this equation, is going to be s over s squared plus omega 0 square. Again, real part of s is greater than 0. So that is the Laplace transform of a cosine signal by using the definition that we learned. So this is how you obtain the Laplace transform of a time domain signal. This is the one way to do obtain the Laplace transform of a given signal. Actually, there's a shortcut in your textbook, table 4.1 in your textbook. There's a Laplace transform pairs. So by looking at these pairs, you can find out, this result easily. And let me see whether I can find something for you guys. Okay. Hold on, please. Merhaba arkadaşlar.
Hocam.
Yani üniversitede internet, elektrik gitti. İlk önce elektrik gitti, sonra internet gitti diyelim. Sizde öyle bir şey oldu mu?
Olmadı hocam.
Olmadı. Bostancı tarafında en azından.
Okulunki daha iyi diye şey yapıyoruz ama böyle sıkıntılar oluyor. Neyse arkadaşlar, bir bakayım. Telefondan bağlanıyorum. Bir dakika bakalım internet geldi mi? Şu an geldi mi? Sesim geliyor mu?
Hocam sesiniz geliyor. Ekran yok şu anda sadece.
Tamam, şimdi telefondan üniversitenin internetine geçtim.
Hocam üniversitenin interneti geldi sanki şu anda. Bende de demin gitmişti ama kayıt devam ediyor. Onda sorun olmamış. Şu an normal.
Tamam, ben de bağlandım. Devam edelim arkadaşlar. Bu tablodan bahsediyordum. So you can look at this table 4.1. We already have this kind of, results in this table that you can look at just these pairs and find out the Laplace transform of a given signal. Okay, so far we transform a signal from time domain to the frequency domain. Now we're gonna learn how to convert back from frequency domain to a time domain. So that's why we need to learn the inverse Laplace transform. Inverse Laplace transform. So there are many ways to do that, but the method that we're going to use is called partial fraction expansion. So it's called PFE. PFE. In Turkish is basit kesirlere ayırma. Partial fraction expansion. Fraction expansion. Okay, let me give an example. Let's say we have an f of s, which is already in frequency domain, s domain. Let's say it's 7s minus 6 over s squared minus s minus 6. The question is, find out the time domain of this, which is the Laplace, inverse Laplace transform of f of s. So we have the f of s, which is equal to this, and the question is, find out the inverse Laplace transform of this signal. In other words, convert back to the time domain. So as I said that we're going to use the partial fraction expansion method, which is equal to, so if I divide this into s plus 2 minus s minus 3. So if I expand this in partial fraction, it's going to be equal to k1 over s plus 2 plus k2 over s minus 3. So now we need to find out this k1 and k2 using the partial fraction expansion. Basit kesirlere ayırma metodu. So how do we find out? K1 is equal to K1 is equal to 7s minus 6 over s minus 3 and then we're going to evaluate for s minus 2. So if I plug in this value to there, it's going to be minus 14 minus 16 over minus 2 minus 3. And the result is minus 20 over minus 5, and the K1 is equal to 4. This is how we find out the K1. Similarly, we're going to follow up the same steps for K2. So then we are going to evaluate for when the S is equal to 3. So if I plug in 3 in the equation, it's going to be 21 minus 6 over 3 plus 2. And the result is going to be 5. So the last step, we're going to, actually not last step, we're going to put back this value into this equation. Therefore, f of s is equal to
Hocam
K1
3
is
olacak ama. 5 değil de
Hangisi?
3 olacaktı sanki.
s equal to, doğru. Thank you. Is equal to 3. So 4 times s over 2 plus 3 over s minus 3. Now we are ready to convert back to the time domain. But for that, we're going to use the table 4.1 in your textbook that I just mentioned. Let me see, I can share it here or not. And Laplace. I guess it's here. Can you hold on, please? Can you see my screen now? Oh, this is for the Z transform.
Yes.
Yes, we can.
Okay, this is for the Laplace transform that I was mentioning in your textbook. So in this case, our terms looks like this one, right? Let me know where is the color. Okay, so this is the pairs that I was talking. The left one is for the time domain signal, and the right column is for the corresponding Laplace transform. So as you can see from here, now our finding looks like this one. So that means the inverse Fourier transform of this signal is going to be exponential lambda t times u of t. So we're going to use these pairs to convert back this signal from the frequency domain to the time domain. Okay.
Sir, will we be allowed to look at this table in the exam?
Yes. I provide you all these tables to you. You don't have to memorize. Okay.
Okay, thanks.
All right. And let me go back to my lecture notes. Okay. I guess you see now. So use actually pair number 5, it was right. Use the pair number 5 in in table 4.1. And according to this one, it was, remember, exponential lambda t ut has a Laplace transform of 1 over s lambda. Okay. So if we use this property from that table, then this is gonna be looks like 4 times 1 over s plus 2, right? Plus 3 times 1 over s minus 3. So according to this one is gonna be 4 times exponential minus 2t, right? Plus 3 times, of course we don't forget the u of t, plus 3 times 1 over, not 1 over, 3 times exponential 3t ut, right? So the result is, the inverse of this signal is going to be 4 times exponential minus 2t plus 3 times exponential 3t u of t. So that is the inverse Laplace transform of this signal. Okay. I just want to put a side notes. So if f of s has a p of s over q of s form, the roots of p of s is called zeros, system zeros. The roots of q of s is called poles. So when I say zero of the system, these are the roots of PS. When I say poles of the system, these are the roots of the Q of S. Okay, so let's have another example. After.
So shouldn't we try to avoid the poles in general, because that will make it division by 0?
Say again, please.
Shouldn't we try to avoid the poles, since that would
No.
lead us to divide by 0?
No, I mean, these poles and zeros are used when you design a system that we're going to see later on in application.
Okay.
They have the rules when you select the poles of Q of S and zeros of the P of S, like a digital filter. Okay. F of S is equal to 2s squared plus 5 over s squared plus 3s plus 2. And the question is, what is the, tap into this. The question is, what is the inverse Laplace transform of this signal? Okay, you guys know what to do now. To use the partial fraction expansion in order to obtain the inverse Laplace transform of this signal. Okay, let's start together to solve this problem. F of s is equal to 2s squared plus 5 over s squared plus 3s plus 2. So the problem, we need to expand to the fraction to s squared plus 5 over s plus 1 times s plus 2. This is a special function which we call improper function, right guys? This is an improper function. Why? Because since m equal to n, in other words, the power of numerator and denominator are equal. We call such function as an improper function. And look at this guy, because the m is equal to 2, n is equal to 2. That's why this signal is an improper function. So since it's an improper function, we need to sorry, we can write down this in the following form, which is bn plus k1 over s1 plus k2 over s plus 2. So what is the bn in this case is equal to 2. How do we find out? Is the coefficient of the highest power in the numerator. What's the highest power in this case? Is the s squared. What's the coefficient of that? Is 2. That's why bn is equal to 2. 2 plus k1 over s plus 1 plus k2 over s plus 2. Okay. Now we need to find out these unknown, which are k1 and k2. You guys know how to do it, so let's do it together. K1 is equal to 2s squared plus 5 over s plus 2 when the s is equal to minus 1. So if you evaluate this equation for s equal to minus 1, it's going to be equal to 2 plus 5 minus 1 plus 2, and the result is 7. Similarly, the k2 is equal to 2s squared plus 5 over s plus 1 when the s is equal to minus 2. If you evaluate this equation when the s is equal to minus 2, it's gonna be s plus, sorry, 8 plus 5 over minus 2 plus 1, and the result is minus 13. So therefore, if you plug in this k1 and k2 value into the equation, we end up with f of s is equal to 2 plus k1, which was 7 over s plus 1, minus 13 over s plus 2. Okay, so we expanded using the partial fraction expansion method. Now we are ready to convert back to the time domain using the pair number 5 in your table. Right, guys? So in 4.1. So it's equal to actually this is gonna be equal to 2 times 1. Remember, we find out the 1 plus 7 times 1 over s plus 1 minus 13 times 1 over s plus 2. Okay. So for this, 1 is actually delta t 2 times. For this one, plus 7 times and exponential minus t ut, and this one was minus 13 times exponential minus 2t ut. That is the time domain signal. So if you reorganize this signal, is 2 delta t plus 7 times exponential minus t minus 13 times exponential minus 2t ut. That is my result. Okay. Any questions so far? Okay. So what we learned so far is to find out the the Laplace transform of a signal in time domain, and then the inverse Laplace transform in order to convert back a signal in frequency domain to time domain. Now, this Laplace transform eventually is an operation, so this operation also has some important properties. So the next topic is going to be some properties of Laplace transform. Let's learn together what are these properties. The first one is time shifting. Time shifting. Let me explain. If we have a time domain signal, f of t, and the corresponding Laplace transform is f of s, then for t0 greater than or equal to 0, then let me write down this way. Then for t0 greater than equal to 0, if I shift this in time by amount of t0, what's the effect of this is going to be in the frequency domain? The effect of this time shifting is going to be a phase shift in frequency domain. Let me highlight this for you guys. So if I shift this signal by t0, the effect in frequency is going to be this phase shift in frequency domain. So a shift in time domain is going to be an effect in frequency domain in the form of phase shift, as you see. Let me give you an example. Example for this property. Example. So, example is this. We already know from the table as well. Exponential a times t as f of s equal to 1 over s plus a. So the question is, if I shift this time signal by t0 amount, that means t minus t0 is equal to exponential exponential minus a t minus t0, right? So instead of calculating this new signal, I'm going to use this property just to quickly calculate the corresponding transform. So which is according to this is going to be f of s times exponential minus st0, right? So the effect of this time shift is going to be a phase shift in the frequency domain. Because of this, t0 is going to be this effect. If I don't know this, if I don't use this property, then I have to calculate all this integration that we did together, guys. So if you know this property and how to use it, then you can easily and very quickly calculate a new time domain signal, the corresponding Laplace transform of a such signal. Otherwise, you have to go through all this messy integration to calculate. So that's the first property. The second one is, second property is frequency shifting. It is the same operation, but now the shift is going to be in the frequency domain. Frequency shifting. If f of t, again, has a corresponding Laplace transform of f of s, then if I shift now the f of s by amount of s0, this effect is going to be f of t times exponential s0 times t. So it's kind of an opposite effect that we just learned. And let me highlight for you guys. So now we said that we have a shift by amount of S0 frequency, hertz, for instance, and the effect of this a phase effect in the time domain. Okay, so let's have an example for this to understand further. So the example is if I have the cosine signal, my f of t is equal to, let me write down here, f of t is equal to cosine bt u of t, has a Laplace transform of, according to the table that we're going to look at, f of s is equal to s over s squared plus b squared. So now the question is, if I shift this by amount of a, what is going to be the corresponding time domain? So that's the question. I have these transform pairs for the cosine. If I shift the frequency domain by amount of A in frequency, what is going to be my new signal in time domain? So according to, either you have to do all this calculation from the beginning to the end using this definition of the Laplace transform, or to use this property. So according to this property, the effect is going to be f of t times exponential s0t. That's it. So fs plus a is equal to s plus a over s plus a square plus b squared, right? So according to the definition property, the result is going to be cosine bt u of t times exponential minus at. So that is the result. If you know this property, you can easily and quickly calculate. Otherwise, you have to go through all this integration. Okay. So the third property is going to be time differentiation. How to take a difference in time domain, differential in time domain. If I have a pair of f of t corresponding f of s, then if I take the first derivative of time domain signal with respect to t, the effect of the differentiation in time is going to be multiplication with f of s minus the initial conditions. That's the first differential. If I take the second differential, this effect is going to be s squared times f of s minus s times initial conditions, the differential of initial conditions, and so on. If I generalize this differential to the nth order is going to be s power of n times f of s times s to the power of n minus 1 initial conditions Sn minus 2 differential of initial conditions, and so on up to Fn minus 1 initial conditions. So this is the effect of the, if you take a differential of a time, differential of a signal in time, the effect is going to be multiplication with the s. Let me highlight for you guys. So this is the effect. If it's the first order, which is hidden here as a 1. So that was the first order. Then this has a multiplication with S1. As a second order, it has this multiplication. If it's an n-order differential. It has this multiplication with the s to the power of n. And the rest of them are actually the initial conditions. If you make them equal to 0, so you just multiply with the s depending on the order of the differentiation. So that was the third property. Now let's look at the fourth property. And after that, we're going to have a 15 minutes break. So the fourth property is called time integration. Time integration. Okay, so that means if I have an f of t time domain signal and the corresponding Laplace transform of f of s, then if I take the integral of this f tau ft dt, the effect of the integration is going to be division by s. So remember from the previous property, if you take the differential, you multiply with the s. If you take the integration, you divide by s. Because integration and differential, they are inversely proportional, right? So that's the effect of the integration in time. And the last one actually, before the break, of course, it's called scaling property. If you scale a signal in time, what's going to be effect? If my time domain signal has a Laplace transform of f of s, then if I scale this signal by amount of a, the effect of this scaling is going to be 1 over a times f s over a. So let me highlight for you guys. Scaling in time has this effect as well as this effect. So this is the effect of scaling in time. Okay guys, let's have a 15 minutes break and we'll be back at 3 p.m. Okay, guys, we are back. Let's continue with the property of Laplace transform. So we left at time scaling. Can you hear me, guys?
Yes, we can hear you.
Okay. The last property is gonna be time convolution and frequency convolution. Okay, my pen does not work. Sorry about that. Okay. Time convolution and frequency convolution properties. Okay. Let me explain. If we have an f1 of t, the corresponding Laplace transform of f1 of s, and similarly we have f2 of t, the corresponding Laplace is f2 of s, then the time convolution says that if I convolve this f1 of t with f2 of t in time domain, this is gonna correspond to the multiplication of f1 of s with f2 of s. Okay, convolution in time correspond to the multiplication in frequency domain. Similarly, frequency convolution, if I convolve these two signal in frequency convolution, this is gonna be correspond to the multiplication of f1 of t with f2 of t. Okay, let's give an example. This is very useful property that we're gonna use from now on a lot. So the question is, I have f1 of t, which is exponential at ut, and f2 of t is similarly fbt times u of t. The question is, what is the convolution of these two time domain signal? Remember, guys, there are many ways to calculate the convolution. Remember from the last week, there's a convolution integration that you need to go over. This is the first way. The second way is to use this property and calculate easily. So let's do it together. According to this property that you just learned, solution. According to the property that you just learned, it says that the convolution of two time domain signal correspond to the multiplication of this in frequency. So I'm gonna just find out the f1s and the f2f and then multiply. So what is the the Laplace transform of f1 of t according to the table that you just learned? pair number 5, it is equal to 1 over s plus a, right? S minus a, sorry. S minus a. Similarly, f2 of t exponential bt ut has this f2 of s, which is equal to 1 over s minus b. So according to this, the convolution of this two time domain signal is equal to multiplication of these two, which is s minus 1 over s minus b, right? Actually, this is equal to 1 over a minus b times 1 over sa minus 1 over s minus b. So we need to apply the inverse Laplace transform. Remember, according to the why it doesn't work? The pen doesn't work. Sorry guys, my pen. Hold on, please. Trying to fix my pen. Okay, it's back. All right, so we need to find the inverse of this, which is gonna be 1 over a minus b times exponential at minus exponential bt times u of t. So that is the convolution of f1 of t with the f2 of t. So if you know this, how to use this property, you can easily calculate the convolution of to signal in time as well as in the frequency domain. Okay. Any questions so far? Before we move to another topic. Okay, why we are learning this Laplace transform? Our main objective in this course is to analyze the behavior or dynamics, eventually the response of a system. So remember, one of the response was from the previous lecture was to find out the zero state response. So we're going to use this Laplace transform to find quickly the zero state response of a system. Okay, so the next topic is zero state response. In this case is the transfer function of LTIC system. Okay, the transfer function of LTIC system. Let's consider nth order LTIC system with, how do we define a system? Remember from the previous chapters, is to use differential equation, which was, remember, Q of t times y of t is equal to polynomial P of t times input signal f of t. Remember, guys, it was f of t. Now we have the y of t, and the impulse response of the system was h of t. This is the time domain, right? So now we're going to obtain this in the frequency domain, which as an h of s is system transfer function, f of s is the input, y of s is the output. This is frequency domain. In other words, is the S domain. Okay, let's go back to the differential equation for a system. D to the power of n plus an minus 1, d power of n minus 1, blah blah, a1d plus a0 y of t is equal to bn times to the power of n plus bn minus 1 dn minus 1 b1d plus b0 f of t. And in this case, all the initial conditions are equal to 0. Initial conditions are 0. Okay. F of t is causal. So that means initial condition of input signal also are equal to 0. Then let y of t has an Laplace transform of y of s, and similarly f of t input has a f of s transform, and because of zero initial conditions in this case, the differential of, remember, fourth order differential of y of t is equal to SR times y of s, using the property we just learned today. Similarly, the differential, kth order differential of f of t is equal to has an sk times f of s. So, therefore, as a result, it's gonna look like s power of n plus an minus 1 s n minus 1 a1s plus a0 times y of s equal to bm sm plus bm minus sm minus 1 plus b1s b0 f of s. So if I take this to the other side, y of s is gonna be equal to bm sm plus bm minus 1 sm minus 1 b1s plus b0 over sn plus n minus 1 n minus 1 a1s plus a0, right? Times, of course, f of s. So we call this, let me highlight with the red color. This we call as a P of s, and that's called as Q of s. So that means y of s is equal to P of s over Q of s times input signal f of s. So also this is called h of s, which is equal to P of s over Q of s. And we call this as a transfer function of LTIC system. So this is how you find out a transfer function of a given LTIC system, by calculating the h of s. So let's continue. By using this actually transfer function, input is f of s, output is y of s. So as you see from here, it says that the input and output has the following relationship. The response of an LTIC system is equal to transfer function times input signal. So this shows the relationship between the output and input. Okay. And it makes sense because remember, guys, at the beginning we have this time domain, which was h of t, and input was f of t, output was y of t. And according to this one, y of t was equal to the convolution of h of t with the input f of t. So which this has, guys, a Laplace relationship, because the convolution in time corresponds to the multiplication in frequency domain. To summarize, so if I give you a differential equation, you're gonna find out the transfer function of that system using this h of s is equal to p of s over q of s. And then from that you can find the response of such system for a given input signal. Let's do an example together. How to find out transfer function of a system, as well as the response of a such system for a given specific input. Example. Okay. The question says that find the response, which is y of t, of the following LTIC system. What's the LTIC system that is given? Differential equation d squared y dt squared plus 5 times differential with respect to the dt plus 6y of t is equal to df over dt plus f of t, and input signal is f of t is equal to 3 times exponential minus 5t ut. Another information, all initial conditions are 0. In other words, the system is in 0 state. Okay. The question says that find the response of the following LTIC system. What's this LTIC system? Differential equation is given d squared over dt squared plus 5 dy over dt plus 6y of t equal to df over dt plus f of t. And the input signal is 3 times exponential minus 5t ut. And lastly, all the initial conditions are 0. So under this condition, please find out the response of such system. Solution. Of course, the straightforward is to multiply, actually convolve this signal, but how we're going to convolve, and we need to find out the h of t first, right? And so on. Okay, so let's convert this into the form of d operator, which is d squared plus 5d plus 6 times y of t is equal to and d plus 1 times f of t. Remember guys, that was the q of d and that was the p of d in time domain. P of d. So the first thing we need to find out the h of s. So the q of s, you just replaced with the d with s. Similarly, p of s is gonna be similarly if you replace the d with the s. So then q of s is gonna be equal to s squared plus 5s plus 6. And then p of s is gonna be s plus 1. According to the definition, we said that the system transfer function is gonna be equal to ps over q of s, right? So that means the system transfer function is equal to s plus 1 over s squared plus 5s plus 6. Right? So this is my transfer function of the system in frequency domain. So the next one, I need to find out the Laplace transform of the input signal, which is f of s is equal to and Laplace transform of 3 times, what was that? Yeah, 3 times exponential minus 5t ut, right? According to the table that I show you guys, if you use this table, the corresponding Laplace transform of this input signal is gonna be 3 over s plus 5. That's my input signal. Now I have the transfer function and I determine the Laplace transform of the input signal. Now I'm ready to obtain the corresponding response or the output of the system, which was equal to, remember guys, h of s times f of s. Let's plug in together. It's going to be equal to 3 times s plus 1 over s plus 5 times s squared plus 5s plus 6. This is my output. In other words, response of the system, zero state. So, but I need this response in time domain. That's why I need to convert this back to the time domain using what? Inverse Laplace transform. How am I gonna achieve this? Is using the partial fraction expansion, basit kesirlere ayırma metodu. So let's do it together. And this is gonna be y of s is gonna be equal to 3 times s plus 1 over s plus 5 times s plus 2 times s plus 3. Then this is equal to k1 s plus 5 plus k2 S plus 2 plus K3 S plus 3. If you follow the similar step that I just taught you guys, you find out the K1 and K2. So you're going to end up with the K1 to be minus 2 over S plus 5. K2 is minus 1 over S plus 2. And K3 is going to be 3 over S plus 3. And using table 4.1, the inverse Laplace transform of this output is going to be equal minus 2 times exponential minus 5t minus exponential minus 2t plus 3 times exponential minus 3t times u of t. And this is my response, the output of a system for a given specific input. So this is how you find the system transfer function and the output of the system for a given specific input. Okay, any questions so far? Is it clear? Okay, the last topic for today is going to be about block diagrams. You guys know these block diagrams, I guess, very well. Block diagrams. You know, when you do a project or do something, you first draw the block diagrams to show the high-level system design, right? So that's why we need to, you know, eventually most of the computer and electronic systems, they are large complex systems. So we need to divide these into the blocks, even some sub-blocks or subsystems, so that you can analyze it. It's really hard to analyze a large computer system within one shot. So that's why we you know, split this large system into the subsystem and, you know, small pieces basically. But how are we going to do that in terms of, you know, a signal sense system perspective? In other words, from the mathematical perspective, how do we split or represent such large system with the small pieces, small subsystems? There are some, you know, notes that I'm going to take. Then I'm going to show you different types of interconnection of this subsystem. First, we said that large systems may consist of a very large number of components. I don't know, some, you know, smartphones eventually is a small kind of looks like a system, but you know, when it comes to design, it consists of I think it's thousands of components, right? So a smartphone actually is it works based on these thousands of components, subsystems. But the question is how these thousands of, subsystems, they are interconnect to each other so that we come up with a smartphone. Analyzing such large systems all at once could be very complex, right, guys? So, and just to give an example, smartphone consists of thousands of components, so, and they're interconnect to each other. It's really difficult to analyze such large system within one shot or at once. So in such case, it is convenient to represent a system by suitably interconnected subsystems, each of which can be analyzed easily. So the solution actually is to represent a system with suitably interconnected subsystems and then basically split into the small subsystem and then analyze each of these subsystems separately. So such approach is gonna be more convenient than analyzing the whole system at once. So the question is then, subsystems, we divide this large system into the subsystems, many subsystems. Subsystems may be interconnected using 3 interconnection types. So we have 3 major interconnection types. What are those? The first one is the cascade connection. The second one is parallel connection. And then we have the feedback. So we use these 3 main interconnection types when we split a large system into the subsystems. Okay, let's describe these 3 interconnection types. Remember, this is our system H of S. This is the large system, the input and the output. So this is our large complex system. So the first one is actually cascade. So how can we give an example? Let's draw it together. So this is my first subsystem. And then this is the second subsystem. And this is the output, the input and intermediate output. So this is equivalent to this following system: H1 of S times H2 of S. This is y of s. This is the f of s. So this is my subsystem 1, subsystem 2. This is the large system. So according to the definition, y of s over f of s is equal to w of s over f of s times y of s over w of s, which is going to be equal to h1 of s times h2 of s. So this is, as you can see, a w of this is equal to h1 of s, the transfer function of first subsystem, and this is the transfer function of second subsystem. And actually, these can cancel each other, and you end up with the original large system. Okay, this is called cascade connection. Of course, here I just show you in terms of two subsystems. You can split this large system into n times or many times subsystem, right? Okay, so the second type of interconnection is called parallel connection. Parallel. Let's give an example. Same example. If I divide this into two subsystems with h1 of s, h2 of s. This is my input f of s. They're going to add them up each other. And the output is y of s. This is equivalent to the f of s, h1 of s plus h2 of s actually, which is equal to y of s. This is called parallel connection. And the last one is the feedback connection. What is the feedback connection? It looks like this. I have input of f of s. We have a summer here. It's sum up or subtract. I have g of s. And then I have a feedback here, h of s. This feedback goes to here. And this is the output y of s. This feedback system is equivalent to this following system, which is g of s over 1 over g of s times h of s, and the output is y of s. Okay, these are the three main interconnection when we analyze or design a large system. Okay, so any question? All right, so that's all for today, and I'll see you next week.